So, hello friends, welcome to all of you. And in this tutorial, in this coming tutorial, we are going to learn different aspects of the algorithm used in OpenFOAM. Okay. So there are three kind of algorithm generally used in OpenFOAM, that is simple scheme, PISO scheme, and PIMPLE schemes. There is another type of the simple scheme, that is the simplex. Okay, so we are also going to discuss that is what is the difference between simple and simplex, and we are also going to do derivation of the simplex scheme. First, I will going to start with the simple and simplex, then we will go to the PISO and PIMPLE aspect of the algorithm. So if you remember that I have told you that in incompressible flow type of solver, we solve these equations where the every term has been divided by the row. And also we are here not considering the body forces. So we are assuming that there is no body forces. So this is the equations we solve for the incompressible flow. And if you talk about the simple scheme, then this transient term will also not present here. And also, since we are assuming the density constant, so there is no need of any energy equation to. So if you remember that in row simple form, I told that how this row has been treated in using the energy equation. Here we are not considering any row term. So this is the equations we are going to solve in the simple scheme without the transient term here. Now there are two questions that is related to simple form. So first question, that if simple form is a steady state solver, then what is the time step in control limits? So this is the questions that is generally asked many times. The answer is simply is that this is the iteration number. So the changing the time step in the control limit will not going to affect the solution in the simple form. Okay, so because there is no transient term, that's why the time step has no any effect on the solution of the final solution of the simple form. Okay, so to understand this, what is this iteration number and how this will not affect the solution, let's go to the terminal and understand this answer. If you have already understand this, then you can skip the video and go to the second question. So I have taken this test case of the pits jelly from the simple form, and I am going to show you that what is there in control dict. So this is a block mystic for meshing file, and this control dict is that is everything related to the time scheme. Okay, now here if you see, this is the start time, so this will start from the 0 and this is the end time, and delta t is 1. In a way, for simple form, we can say that the number of iteration it will take from 0 to 2000. Okay, because delta t is 1, so every time it will march for one time step. It means that it is iterating over one times. It means that it will run for the 0 to 2000 number of iterations. Okay, now if you put 0.1, then the number of iterations it will increase. So either it will run for this number of iterations or it will converge earlier. So even if you change the number of delta t, it is not going to affect the value. Second is that is under relaxation is necessary in simple form, and if yes, then why? Okay, so the reason is that while we are using the correction field for the velocity field, for that purpose we are ignoring the contribution of the neighboring field. That is the reason we require the relaxation. Okay, now I think that you are confused here, so let me again revise the simple form. After that, we are going to also derive the equation for the simplex algorithm. Then after that, we will go to the PISO and PIMPLE form. Okay, so this is the complete outline of this tutorial. So this is the algorithm we have talked about. So here you can see that this is the present cell we are talking about. This is the neighboring cells, and this is the body force, and this is the pressure field. Okay, so while we are talking about this UP, so you will remember that we form a This equation can be written as the UE equations in OpenFOAM. So when we talk about this UE equations, so the matrix can be decomposed into the two forms, that is the UE equation.h and UE equation.n. So now let's understand that where we are ignoring this neighboring term. Okay. So this is the velocity characteristic. Okay. So if you write these equations in the form of the velocity character, if we write this step here, so you can write it as a APU into UP minus HU equal to minus P del P. So this is the equation we can write in the form of HU. Okay. Now if we write the corrector equation for this, so this is, it can be written as APU UP dash minus HU dash equal to minus del P dash. Okay, so this is the characteristic. Okay. So if we update the UP, so the update step will be UP equal to UP equation that we are predicting from the momentum equation. So this is the equation we are predicting from the momentum equation, plus there will be some corrector. Okay, so this is the complete equation for the update of the UP equations. Now if we write here UP equal to, so this UP star will be given by same kind of equations. So this UP star I can write here that HU star. Okay. So this HU star upon AP. So this APU will go to the divide here minus del P star upon AP. This is the UP star, plus there will be U dash. Okay. So for U dash also we can write as a HU dash upon AP U minus del P dash upon APU. So this is the pressure character velocity characteristic. Here we are ignoring this character for the neighboring cells. This you can match as that. This term is HU upon APU will this term, and this minus del P upon APU is the combination of these two terms. So you can see here that we are ignoring the corrector step for the neighboring cells. You can see here that correction in the velocity is completely depend upon this pressure correction step. Okay. So sometimes it happens that suppose that the correction in the pressure is very large. So if the correction in the pressure is larger, then it is going to update the velocity in the large amount. But this pressure term is only depend upon the one equation, that is the continuity equations. So if this large correction in the pressure affects the velocity also, so this velocity, update velocity is not going to follow this is the momentum equations, which means that the correction in the velocity will require to only change by a smaller step. Therefore, there is a requirement of the relaxation factor in the simple scheme. Now, what is the relaxation factor? So suppose at iteration 1 we are getting pressure equal to 5, okay, and at iteration 2 we are getting pressure equal to something like suppose 25. Now if alpha, that is relaxation factor, we are taking at as a 0.3, suppose we are taking the relaxation factor is around 0.3, then P will be 0.3 multiplied by 25 plus 0.7 that is the 1 minus 0.3 is equal to 0.7 multiplied by 5, that is around 11. So you can see here that the larger change in pressure field can be avoided by using this relaxation factor. Okay, so this iteration 1 was giving the pressure value around 5. Now this iteration 2 was giving the pressure value around 25. But if we use a relaxation factor of around 0.3, this is giving the value around 11. So this is the concept of the relaxation factor. So the strange change in the pressure or larger change in the pressure avoided by using the relaxation factor. So I hope this concept of the relaxation factor is understood by you. So here we are updating the U. So while we are updating the U, we are ignoring the contribution of neighboring cells. Okay. So that is why it is important to understand that whether we can ignore the contribution of the neighboring cells or not. Then we will understand why simplex is necessary. So this is the equations we are solving. So after solving the momentum equation, suppose after solving the momentum equations, we are getting this U star. But this U star will satisfy the momentum equations, but not the continuity, because we are getting the solution for the momentum equations. Okay, and why this will not solve the continuity? Because the pressure gradient, this is the term of pressure gradient. The values in this pressure gradient, we are taking some values from the previous iterations. Okay, so therefore there will be required some corrections, and these are the corrections. So we are correcting the U and we are correcting the P. Okay, and this is a correction field, and this is a correction field for the pressures. Now let's go for the continuity equations. Okay, so if we write m dot f, okay, so in m dot f there will also require some corrections because we are correcting the U. So the mass flux at the faces, so mass flow rate we have to calculate at the faces. So this is the mass flow rate based on this U star that we have got after the solving this momentum equations. This is the mass flow rate after the solving the momentum equation. So to apply the mass conservation, there also required some correction. So this is the correction. If this is a cell, okay, so this is the SF, the normal face surface is the SF, and this is the correction velocity, and this is the constant density. Okay, so we can write it as a m dot f plus m dot dash. Okay, so I think you can relate here. But this is the mass flow rate after solving the momentum equations, and this is the mass flow rate due to the correction field. So if we take a cell center, so this will be east and this will be west. So for this cell center, the continuity equation we can write it as a me plus mw, that is equal to 0. After applying the correction term also, we can write it as a m dot e star plus m dot e dash plus m dot w star plus m dot w dash. Okay, that should be equal to 0. M dot e dash plus m dot w dash equal to m dot star plus m dot star, so whole term equal to negative. This is the continuity. So this is the very interesting observation. Okay, so we observe that once we reach at the final solutions, then the correction terms will automatically become to the 0. Okay, so here you can write it as a m dot e dash plus m dot w dash equal to 0. Okay, so this is the very interesting observations that once the solution reaches to the steady state, then the correction error due to the mass will be automatically become the 0. So this will not affect the final solution. Let's derive the pressure correction term. Okay, so this same equations we can write as a UE plus H dash U equal to B capital BU minus DE into del P upon del X into E. So if we correlate this complete equation with this equation, so you can observe here that this complete derivation divided by AEU will become this term. This PEU divided by AEU will become this term, and similarly this V upon AEU divided by will become this term. Okay, so these equations is the equations that we are going to use in the further derivation. So suppose after solving the momentum equation, we find a solution that is the UV star. Then this term can be written as the UV star plus H dash U star equal to BEU minus D upon del P upon del X into E. Similarly, for west phase, we will get the similar expression, that is the UW star. So this is the equations after getting the solution by solving the momentum term. Now remember, this is the exact equations. Okay, but we are getting this solution. Okay, so this solution UE star and this UE, they are both not same. Okay, because here this is the exact form of the pressure equation, but here we are solving the pressure equation by taking the values from the previous iteration. Okay, so I mean to say that the correction we should require to do here, that UE dash equal to should be UE star plus some correction is required. Okay, similarly, if UW should be some correction, that should be, we can say that UW dash. Okay, so if we subtract this equation from these equations, then the equation that we will get, that will the correction equation. Okay, what I mean to say that if I subtract UE minus UE star, then I will get UE dash. So from here, similarly, I am going to subtract these equations. Suppose this is equation 2 from the equation 1. So let me subtract it. So if I subtract this UE star minus, sorry, UE minus UE star, then I will get UE dash. Similarly, if I subtract this term minus this term, so I will get H dash into U dash E. Okay, so this B will be cancelled out. Okay, so this will become 0. Now this minus this TE. Now remember that this pressure equation is the exact pressure equation, but here we are solving by taking the values from the previous iteration. So there also required some pressure correction term in this pressure gradient. Okay, so this will be del P dash X. Similarly, there will be equations for the UW star. So this equations, this is the correction in the UE star, and this is the correction equation in the UW star. Now let's put this value into the mass conservation equation that we have obtained. So remember, we have gotten that M dash plus MW dash equal to minus me star plus mw star. That this equation we have already gotten in the v star. If I again draw the cells, this is the cell center, this is the west, and this is the east face. Okay, so suppose here the surface normal vector equal to del ye, and this is the del yw. Okay, so this is the surface area. Okay, let me write first these terms in terms of the uv dash. Okay, so me dot dash I can write here uv dash into del ye dash. So this is the surface flux, mass surface flux on this face. Similarly, there will be correction to the mass on the west side into del y. Now this uv dash and del w dash, we have already gotten the equation in the earlier side. So this value I am going to put in this equation here. So I can write here rho into minus h u dash on the east minus d into del p upon del x dash onto the east into del y dash. So this is the complete system. Similarly, here we can write this as a minus h dash pw dash minus dw del p dash upon del x on the west face into del w dash. That should be equal to the minus me star plus mw star. Okay, so this equation can be written in such form. Now, in this term, pressure appears as a diffusion type of form. Okay, so we can further discretize this pressure terms on the east face and the west face. So now let's discretize this pressure terms and see what happens. So after discretization, the terms of the pressure, we can write it as a rho e minus h u dash e minus this d into pe dash minus pc dash upon del x onto the east into del y. Okay, so this is our cell, and this is the w, and this is the e, and this is the cell. Okay, so this is the central cell C. Similarly, there will be another cell, and there will be another cell. So this is the east, and this is the capital W. So this capital W, capital C, or capital E is representing the cell center. So what we are doing, we want to find the pressure gradient on this face center. So we are taking as the PC minus PE upon del X. Okay. Similarly, if you want to write the next term, that will become rho E into minus HE. Sorry, here it will be UE. UW dash minus D, that will become PW minus PC dash on del X on W into the del Y W equal to minus M dot star E plus M dot star. So if you do rearrangement here, you can write this complete term as a So this is the complete term we will get after rearranging it. Okay, so we can rearrange this equations. We can rearrange this equation. So we will get this kind of equation here. So if you further rearrange these terms, you can write these terms as a into the form of the coefficient. Okay, so you can write it as a APP dash into PC dash plus AE P dash plus P dash E equal to, sorry, AWP dash plus PW dash equal to BCP dash. So this, in this form you can write the above equations. So if we compare this equation with this equation, suppose this is the equation, again 4 equation, and this is the equation 5. So if we compare the equation 4 and 5, the coefficient of the different terms AP dash, AE dash, AWP dash and BCP, you can write it as a, so if we write the coefficient, we can write in this form. So we compare just equation and you can write the coefficient here. Now you observe that this again the correction term of the continuity equations. So we have already proved that this will become equal to 0. So this term will automatically become to the 0 when we reach to the final solution. So therefore in the correction term, we in simple form therefore in simple form in the correction terms, we automatically from the starting iteration we start with assuming that this term will be 0. I told you that while we are updating the velocity, we are not considering the neighboring, we are ignoring the neighboring field. So that is the reason why we can assume these assumptions. Now I think you have idea that why these assumptions can be taken in the simple form, and this is the, there is another assumptions where we are considering these neighboring terms while correcting the u, and that is the simple terms with the consistent. So but remember here that this assumption only can be assumed once we reach to the correct final solution. Okay, so once we find the exact solution, then only we can assume this kind of assumptions. Therefore, since simple form is steady state solver, in simple form we can assume this kind of assumptions. In transient algorithm, we cannot assume this kind of assumption here. So I think this idea of ignoring the neighboring field in the correction field has been understood by you. Let's go to the understand why simplex algorithm or the simple with the consistent is required. So again, let's start with this equation. In simple term, we are correcting the velocity. We are ignoring the contribution of the neighboring fields. Okay, but in simplex, we are not ignoring this term. Instead of ignoring it, we are saying that let's calculate the velocity of the V cells. Okay, so VC. So here it is the east. So if I drew these cells, so this is the C I am talking about. So if I want to predict the velocity at this cell center, so I am writing C VC dash. Okay, so to correct the velocity field of this center cells, I am taking the weightage average of the neighboring cells. So what I am doing is that I want to correct this velocity, that is the center cell velocity. So instead of ignoring this contribution of this neighboring cells, I am taking weightage average of the velocity cells in the neighboring cells. Okay. So to find this weightage average of the neighboring cells, I can write it as a AF dash upon B dash F upon AVF, that is the NV. This is the method of finding the weighted average. So now further I can modify it as a FNV. This AF will go this side, left side. So this will be AVF into VC dash is equal to F neighboring cells into AFV into V dash F. Now let's divide both sides by the SCU. Okay, so the SCU is the coefficient of the center cells. So for the cells for which I am solving the equations, so this is the contribution of the SCU. So I am going to divide this complete term with this SCU. Equal to summation of AF NB AFB V dash AF, but again summation of SCU. So here we can take the VC dash out and we can write this both terms in terms of the H operator. So the equation will become HC V dash equal to V dash C into HC1. Okay, so this HC1 I am introducing for the first time. So if we compare the above equation with these equations, see if I compare this equation with the above equations where I have written here, so this will be like that. This HC V dash summation of F for the neighboring cells AFV feed SCV. So this is the HCV dash, and this HC1 will be like summation of F means neighboring cells AFV upon SCV. Okay, so remember that we have divided the both term with this term SCV. So this is the equations that we are going to use for the simplex. Now earlier this is the neighboring cells, contribution of the neighboring cells. So this SCV dash we are ignoring in the simple. So we were ignoring this term in simple while correcting. So while we were correcting the velocity corrector step, so these terms were ignored, but here we are going to consider this term only by this approximation. So we are going to use this approximation, that is the SC V dash equal to V dash C into SC1. So this approximation we are going to use in the simplex term. Okay, so recall our equations. So the corrector term were like that: V dash plus H dash into V dash, so this will be modified. HC V dash equal to minus D this into del P dash. So these were the equation for the velocity corrector step. So in earlier simple schemes we were ignoring this term, and why we were ignoring this term that I have already explained you. Okay. But now in this examples in simplex algorithm we are going to consider this term also by this approximation. So this approximation I am going to use. So in place of this place I can write this term. So this will become as the V dash C into 1 plus HC1 equal to minus into del P dash into C. So this is the corrector step that we are going to use in the simplex. Simplex, simple plus consistent. Now this same term I can write further. So this I can write that as a VC dash equal to minus D CV, and there is some bar, and that is a del P dash into C. So here this you can write del CV equal to dCV upon 1 plus SC1. Okay, so this is the corrector step for the simplex. These same expressions we can find out in another way. So let's see how. Let me revise the equations that we are using from starting. So that is the ACB into the contribution of the neighboring cells. So that is the AF into V into BCV minus VC into del P. That equations we are solving from the starting. Now let's add and subtract this term AFV and VC. In both this side we are adding this term and subtracting the same term. So then we can write it as a ACV plus summation of, this is neighboring, CF neighboring into AFV, and this is the VC. So this is, here we are adding this term, and in the next term, so this AF, here AFV will be common, and this will be VF minus VC equal to, again we can write as a VC into del P plus VC into V. So this thing we are doing, that we are adding this term we are adding once and then we are subtracting once. Now as we used to do in the simple schemes, we used to divide this complete term into the all the terms of this equation. So we can write it as a, this is the AFV into AFV upon, this term will be divided here, and this will become SCV plus summation of FNV into AFV. Okay, now here will be VF minus VC equal to this term. Similarly here we can divide, here we can write it as a DCV, okay, into del P, and suppose VC. So these terms will be transformed into these equations after dividing this coefficient of this VC into the all sections. Okay, so these equations we have got, and similar to earlier we can use the H operator here. So this, for this purpose, this complete term we can apply the H operator. So this equation we can be written into the form of the VC plus SC dash V minus VC. Now this right side will be similar to the what we are writing here. So DC into V into del P plus VV capital VC. Okay, so we can also find out the corrector step for these equations. So the corrector step, these terms will be goes out, and now it can be written it as a VC dash plus HC into V dash minus VC dash minus DCV into del P dash. Okay. So this is the same similar equations as the earlier. If we drop this term, so it will become as a VC dash minus DCV into the del P dash. So this is the similar equations that we have find out here. Okay. So this is the simplex equation, and we have derived in another way. That is also the simplex step. Now you are observing one thing, that in earlier when we were using the simple scheme, we were just dropping the HCV dash. So these terms we were dropping in the earlier simple scheme. Here we are dropping the HC into V minus V dash, VC dash. If you quantify these two terms, this quantification is smaller. So HC V dash minus VC dash is smaller compared to the SC into V dash. So this term is smaller compared to the this SC V dash. It means that the term we were ignoring, the simple scheme, is much more greater than the term we were ignoring in the simplex scheme. That is reason this the conversion of the simplex scheme is going to be the faster than the simple scheme. So the conversion of the simplex scheme is faster than the simple scheme, because we are ignoring the smaller quantity here compared to the quantity we used to ignore in the simple scheme. Also, one thing also we observe that, so whatever you will get after solving the momentum equation, simplex scheme will give the more appropriate solution or more correct solution, because here the quantity we are ignoring is the smaller than the simple schemes. So that I can also write better solution compared to the simple. And this is the reason, because so again I have to write this term. Again, this is the reason, since here we are ignoring the larger term compared to here, so that's why it is not much necessary in simplex to provide the relaxation factor or dropping smaller term in simplex the relaxation now pressure term is unnecessary as compared to simple scheme. Okay, so since we are dropping the smaller term in the simplex, so the relaxation of the pressure term is not as required as the simple scheme. Okay, so I think these 3 points is clear to you, why simplex is faster than simple, and why simplex will give better solution compared to the simple. And this is the another thing, that simplex relaxation of the pressure term is unnecessary compared to the simple scheme. Since the simplex we are solving the, we are not ignoring the neighboring terms, so the computational cost of the simplex will be more compared to simple scheme. So I hope this simplex and simple is clear to you. So I think the concept of simplex is clear to you, and let's see on the Ubuntu terminal that how this OpenFOAM has been treated this simplex kind of solver in simpleFoam. So before this, let me first revise that what we have discussed here. So this is the equations that we are solving, and I told you that the difference between simple and simplex is that simpleFoam did not take the consider of the contribution of the neighboring cells in the velocity characteristic, but in simplex the contribution of this neighboring cells has been taken consideration by taking the weightage average of the neighboring cells. Okay, so this is the steps that we have start, and we can write this equation in the form of this. Now further we have derived the same equation in the form of the H operator here. So this is the H operator. So with these three important equations that we have modified in the simplex, let's go to the derivation for the OpenFOAM perspective. So this is the assumptions that I show you. So the similar equations I can written in the form of the this equations. Now this same approximation in the form of the H operator in OpenFOAM can be written is this form. So this is the similar equations that you can relate from here. So this is the equations that I am writing here. Okay. Now the corrector equations in the form of the H1 operator you can write in this form. So AU dash equal to H1U dash minus grad P dash. Okay. So this is the velocity corrector step. This is the steps that I am coding here. Now if you go to the further, so I've taken this term in the left side. So this term is as we became A minus H1U dash equal to minus grad P dash. Okay. Further I have modified that U dash equal to 1 upon A minus H1 star into grad P dash. And further this complete the corrector equation can be written into form of the AT. So this will become that U dash equal to 1 upon AT into minus grad P dash. This has been modified in the simpleFOAM to make it simpler. So let me revise the algorithm. So what we are going to do. So first we will solve the momentum equation to find out the velocity that is U star. Okay, now this U star is satisfying the momentum equation but not the continuity equations. So this is the similar equation that we have written in the form of the H operator. So this is the similar equations. So there will be no changes. This step will be similar. Only the corrector step there will be modification. So this corrector step we have find out in the last slide. And now this is the equations. This is the U star that we are getting after solving the momentum equations. But there will be some corrector required to find out the exact solution, that is U. So to find out the U, let's write this right hand side in the form of this U star and U dash. So these two equations that I am going to use in the last equations. So if I write U equal to U star plus U dash, so this will be U star that we have gotten, and this is the corrector step minus 1 upon 80 minus grad P dash. Further, if you know that this we have to find out what is the pressure corrector step. Okay, so the pressure corrector can we find out using this equation, that is the P minus P star equal to P dash. So P dash equal to P minus P star that we have uses here. Okay, so this will be grad P minus grad P star 1 upon 80. Okay. Further, if you rearrange this complete equations, then this is the last equation will be written in the same form. So that is the U equal to H U star upon A minus 1 upon 80 minus 1 upon 80 into grad P star minus 1 upon 80 into minus grad P. So this is the complete equation for the velocity corrector. That is the difference between the simple and simplex. Okay. So remember here that if we compare this last equation with the simple, so this term there is no change. So H U star upon A, there is no change. That 1 upon A minus 1 upon 80 grad P star, there is change, and that minus 1 upon 80 minus grad P, there will be some change. So let's go to the terminal and let's see how this term has been coded in OpenFOAM. So I am already in the folder that where we are discussing this all the tutorials. So here I copied one test case from the simple incompressible simpleFOAM, and here the solver simpleFOAM. I have just copied these two folders here. So if I open the test case of the PITS jelly, so you have to go to the FB solutions, and let me open it in the Genie. So here in OpenFOAM, the simplex has been treated using the simplex term in the simpleFOAM. Okay, so there will be if you open the FV solution dictionary, so there will be another sub dictionary, that is the name as the simple. In simple sub dictionary, there is a term called as the consistent. Okay, so if you write this consistent equal to yes, then it will solve the simplex. If you write it as a no, then it will solve the simple form. Okay, so this is the where the solver compiler recognize that what you want to solve. If you want to solve a simplex, then you have to write this yes. If you want to solve the simple, then you have to write the no. Now let's open the solver. So this is the simple solver. So everything will be the same. There will be no any change. Simplex thing, every algorithm is the similar to the simple. Where is the change? This U equation will be also the same. There is no any change we have to do. The change will be there in the P equations. So if you open this P equation in the Genie editor, so remember I told you that this H by A should be changed. Okay, and this U character stuff will be changed. Okay, so what I am saying, so see that everything will be same till here. Now this another variable it is taking, that is the RATU. So that is for the 1 upon 80. So this is the 1 upon 80, and this RAT equal to RAU. So it is storing here, that is the 1 upon 80 equal to 1 upon A. So this is the step that it is doing here. Okay, now it is asking that whether you want to solve the simple dot consistent or not. So if you in the FV solution, if the consistent equal to yes, then it is going to solve this equation. If it is no, then it will not solve. Just go with this RAU value and H by A value. So remember this, if this simple dot consistent equal to 0, means that if the simple dot consistent equal to no, then this RAT equal to RAU. So this RAT and RAU both are the same value. But if this step is yes, then it is going to change the or update the value equal to 1 upon RAU minus 1 upon U equation at H1. So this is the value that it is calculating, 1 upon A minus H1 equal to 1 upon ATU. Okay. Now this 5 H by A, that is something related to the simple dot corrector that not orthogonal. Maybe we can discuss in the separate tutorial. Now this H by A value has been updated. So H by A equal to H by A minus, so here what it is solving. So H by A equal to H by A equal to H by A minus this complete term. So this is the equation that it is solving here. And you can relate from the slide. This is the equation that I am telling you, that H by A minus, this is the 1 upon A minus 1 upon AT into grad P. Okay, so this is the till here. So everything will be same. This, if simple that non-orthogonal is required, then it is going to solve for that purpose. Otherwise, it will go to the P relax, and now here is the update velocity character step. Okay, so remember that H by A step will be this value if you are using the simplex kind of solver. Otherwise, this H by A value will be this value. Okay, so this is the difference between simple and simplex. Here also you can remember that here RATU will be RAU. Okay, so RAT value will be similar to the 1 upon A if you don't use the simple dot consistent. But if you use the simple dot consistent, then this value will be updated here into the FVC dot grade. Okay, so I hope that this step you can relate with the whatever written on the slide. Okay, so this is the same value. So I think now you can relate that what is different between simple and simplex, and every algorithm other steps are similar to the simpleFOAM, which I have discussed in the earlier tutorial. So I think this concept is clear to you. Now the relaxation factor, this simple kind of algorithm, these things should not be confused by you. And since this video has been already too much longer, so I think the PISO algorithm and PIMPLE algorithm I can discuss in the next part of this video. And many people are requesting me to the make a video on the turbulence model or the MRF model. So my approach is to start with the simple things, then go to the advanced level. So that's why first I will explain that how the source term has been treated in the OpenFOAM. Then after those source term treatment explain lesson, then I can go to the this turbulence model or the MRF model, MRF kind of model. So I think you will like this video, and please, if you have any question, then you can ask me in the comment box. And please subscribe my channel and please like this video, and kindly share this tutorial to other of your friends also, because the comments, your likes and the subscription which I get on the my YouTube channel, so that motivates me to the make a new content on my channel. So with this, thank you to all of you. Thanks for watching.